Thanks, Steve. Good morning, everybody. As Steve has said, what I want to talk about this morning is when it can be a good idea and when it can be a bad idea to connect internet exchanges and another layer 2 switch fabric together. As an internet exchange operator, we increasingly face different scenarios where the equipment that the customer is connecting to is not a classic router. Some of the things that we see are ISPs who don't want to spend a lot of money on lots of router interfaces, so they'll have one big router somewhere in their network and they'll have Ethernet switches as a way of aggregating ports into that. Sometimes these port aggregating switches finish up connected to internet exchanges. Remote ISPs who will use some intermediate third party, possibly within the metro area, possibly long haul, to provide something that looks like an Ethernet circuit to connect into the exchange. Increasingly, I think fashionable are what are called distance peering services, where instead of physically locating a router at a data center where the internet exchange is, it may be in a completely different country, and it's being backhauled over some pseudo-wire circuit, typically Martini tunneling over MPLS. Some other scenarios. Quite often the equipment that is connected has actually got layer 2 hybrid bridge and router capability. Sometimes when you ask the ISPs what kind of equipment they have, they don't always know the answer to whether it's a layer 2 or layer 3 device at some of the less clueful ends of the market. Another thing that comes up from time to time is regional exchanges. They don't quite have critical mass. They have this idea that if they somehow cross-connect their exchange to the critical mass of a big centralized exchange, that somehow this will solve all their expensive bandwidth problems in that region. Increasingly, we're seeing carriers less inclined to use SONET SDH type circuits and more to use Ethernet as a way of carrying traffic on a circuit basis. And we're also seeing increased competition and diversity in the internet exchange market. Within a given metro area, you quite often get multiple exchanges. I mean, we have as many as 6 or 7, depending on how you count them in London. So all of this, the reality of being an internet exchange operator in today's market is that basically there's increasing pressure to connect things at layer 2. Okay, it saves money, but is it a good idea in general? Is it a good idea from a technical perspective? Why layer 2 interconnect is bad, to qualify Steve's remark in a bit more detail. Fault detection is a nightmare. I mean, basically, you can either see the interface to the directly attached layer 2 equipment going down, or you can't ping the router at the end of the connection, but you don't actually know if there's anything intermediate failed. With traditional IP ways of doing this, of course, we have good old trace route as a way of doing this. With old-fashioned telco circuits, you can always ask for loopbacks to be placed at intermediate points along the circuit. The worst thing is that this is basically some layer 2 cloud, and you have no visibility into that in terms of what's going on. Loops, broadcast storms, these can impact more than one operator. These are bad enough when they happen on a single layer 2 infrastructure. When they start propagating against more than one, along more than one, in general, there's very little to stop it happening. Some slightly more subtle problems with layer 2 interconnect. Spanning tree. I've been working with spanning tree for over 15 years, and I hate it more each year. Limited and no support for multiple routing domains. There's no concept of autonomous system or separate routing domain or even anything as simple as an OSPF area in most spanning tree implementations. That means that basically if you have 2 layer 2 domains connected together, the idea that you can have multiple connections between them for resilience is just not that simple. The other thing that can happen is BPDUs from one spanning tree domain can get into another operator's network, cause strange stuff. I said in my abstract there have been some well-known incidents at other internet exchanges. Well, we were the victim of one of these on the 6th of May, unfortunately. And basically, BPDUs leaking in, not from another internet exchange, but actually from a customer-connected layer 3 device with layer 2 capabilities, as far as we can tell, basically caused forwarding loops within our infrastructure, and that was quite disruptive. Scaling issues with layer 2 interconnect. You need unique identifiers to start connecting this stuff together. The obvious way to do it is with VLANs. The tag space is only 12-bit. It only has local significance, no globally unique significance like IP addresses or AS numbers. A non-unicast traffic is a nightmare. And then there are also issues in terms of if you use MAC filtering, actually keeping track of the potentially hundreds of MAC addresses that you might see. in a public Ethernet operator, and how you actually filter all these. Bill Woodcock introduced me to this idea of coterminous IXPs. Again, as I said, in today's market, you will typically have multiple exchange operators per metro area. Now, competition can be a good thing in terms of increasing customer focus, driving costs down, increasing flexibility. But if you have too many exchanges competing in the same market, then basically it starts pushing costs back up again. You may, if you're a large operator, find yourself connecting to as many exchanges as you have key peers that you want to peer with publicly. So you can actually split critical mass by having too many of these things. What do we mean by coterminous IXPs? Well, this is my definition rather than Bill's, but I think it fits in with the spirit of his concept. They're in the same, they share one or more buildings, they're in general operating in the same metro area. There is some degree of overlap. You can connect them together using native wire speed media relatively cheaply. Again, cheapness definition may vary, but means minimal active components. In general, what it means is you can run a wire or a fiber from one piece of the building to another to connect them together. And again, the variations of the definitions of cheap in metro area will vary very much depending on the individual market. There's no absolute values of what is a cheap interconnect or what is a metro area. So you've got these two exchanges which are coterminous. What are the advantages of interconnecting to them? In general, most of the participants only need to connect to one exchange instead of two now. That puts their costs down. It means that the two interconnecting exchanges have basically got a critical mass which is much greater than the sum of the parts. Reduces latency, potentially traffic between the two between participants in the two exchanges is not going via third-party transit providers. Less traffic is going out the area, and it means that if you're coming into the area, then potentially the number of exchanges you need to connect to and which ones it's obvious to connect to becomes much simpler. I mentioned that there's all these issues with layer 2 interconnect. They become worse in the non-coterminous situation, where you maybe have two exchanges that are in different metro areas, or maybe not in the same building in the same metro area. In general, you have to use third parties to provide the connectivity. There may be more than one intermediate party. Again, there's all the problem diagnosis issues that I talked about already, the fault finding issues, the broadcast leak and loop issues. And in general, if you're using long-haul Ethernet circuits, then they're much less likely to be transparent than your native circuits. There may be issues with latency, there may be issues with MTU size, particularly if you're using some kind of tunneling technology. There may be some fancy traffic shaping requirements underlying, which are part of the package deal that you got on the cheap bandwidth to connect the two together. And provisioning is generally extremely difficult. I mean, we've had some provisioning exercises where there's been maybe as many as 4 parties Ethernet switches connected together. Not something that you would do except in recent market conditions, but you have to map the MAC addresses, the VLAN tags, the port IDs across all of these, and tracking that when there's no single global registry of any of that information can really be a provisioning nightmare. Broadcast traffic, well, the default behavior of IP layer 3 networks is that traffic forwarding is unicast. The default behavior of layer 2 traffic bridge networks is that traffic forwarding is broadcast. That's a generalization, I know, but basically it means that you have these high pressure hoses which can leak anywhere. Even the largest internet exchanges, if you're seeing more than 100 broadcast packets per second, there is probably something wrong. As a result of the 6th of May incident, I know that today's switches on a 10 gig backbone can forward broadcast packets as high as 100 times that. But of course that will burn out most of the connected routers long before that in terms of CPU resources from handling broadcast traffic. The impact of these kind of situations can be quite wide. I think the point is that I don't think that many people would, in their right minds, connect a public internet exchange to an intermediate Ethernet circuit to a public internet exchange. I have seen some people attempt that, but more importantly, even when legitimate distance peering providers are involved, you don't know what's on the other end. That stuff may come back at you. All of this makes the thing much less scalable. So I've talked about some of the general issues, some of the general experiences, some of the general principles behind this. How did this work in practice? When we went into the practice of connecting Internet Exchange Point and LUNAP, basically we very much took the view that this was a risky thing to do, but there were advantages, so let's try and be as careful as possible and do this right. We're both London-based exchange operators. We have rather diverse approaches to what we do. The markets that we sell to are not the same, but they're overlapping. The single biggest thing that we have in common is we're not the biggest internet exchange in London. We've basically been cooperating on an informal basis for a couple of years now. After some pilot experiments, that led to a formal agreement that we wrote and signed just over a year ago. That's the URL of that agreement. That will come up again at the end. Just to summarise, why are we diverse? What's different about us? Exchange Point, we're a commercial internet exchange operator. We've been around for 3.5 years. In London market, we're now up to 150 customers. We have about 8 gig of total traffic split between our Ethernet switch and WDM networks. We don't just do public peering, we do private peering, transit interconnect, DSL interconnect. It's all backed up by a service level agreement. LUNAP's a more traditional type of internet exchange, not-for-profit membership organisation, been around kind of longer than we have. Less members, less traffic, and the resourcing is very much on a volunteer, best internet volunteer effort tradition, and that's to provide peering as a best effort. Okay, the next slide basically just shows a brief map of the main colo centres in London and the Exchange Point network. Basically, we're in 7 buildings, actually 5 different colo providers in these. The important thing is this coterminus principle, which is that LUNAP is at 3 of these buildings. It happens that it's the 3 largest sites that are connected by our 10 gig backbone now. Exchange Point, we're also doing similar things in other metros in Europe. The important thing, though, is that we're not connecting these metros together. We do not have a pan-European exchange point. We have multiple basically identical internet exchanges in multiple locations. When we looked into this, we basically identified a number of different models for connecting the 2 exchanges together. There's a bit more detail in these in some talks that I've given previously, but essentially we thought there was 2 important models to consider: private peering and shared public peering. And what we did is we did the first and then the second, and then we thought we'll explore the other ones in future. This was mainly to minimise the operational risks. We thought the private peering model would be much less risky than doing the public. But it was also about a confidence building exercise. As I said, like ISPs, internet exchanges compete with each other now, but there's also a need to interconnect. And it was important to build confidence between the 2 organisations that we would not harm our own organisations by doing this. You'll see from the next diagram that diagrams are not my strong point. But essentially, this briefly shows the 2 internet exchanges, a point-to-point VLAN between them. The VLAN basically is on 4 ports, the 2 participants' ports that need to connect, and on the interconnect link. Basically, you have a very simple point-to-point virtual connection there. Next picture shows the second mode of public peering. And the idea there is that you have a VLAN which is effectively a shared logical exchange that exists across the 2 underlying exchanges. In general, people don't take extra ports to do this. In general, they will have tagged using 802.1q sub-interfaces on their router, which allow them to opt into multiple VLANs on their port. One of these VLANs can be the shared public peering VLAN. Where have we got to with this so far? On the point-to-point stuff, that was what we did first. We have about 12 Exchange Point customers, 8 LUNAP members, a total of 28 VLANs on that mesh, seeing about 8 meg of traffic, and basically each one of these VLANs has a /30, which is assigned by one of the peering parties. Having said that this is a much safer way of doing things, it also has a much higher management overhead in terms of configuring up the VLANs and coordinating between the 2 parties. People generally don't find this as convenient, and we haven't seen much growth since we introduced the public interconnect mode. On the public, it's been around for about 9 months now. Very big take-up, 42 exchange point customers, 14 LUNAT members, some overlap with the people doing the point-to-point stuff. About 30 to 40 meg of traffic there, and I mean, we've had a /24 assigned to it. It's a particular VLAN that's shared between the two fabrics. To a lot of intents and purposes, it just looks like another internet exchange from the outside world. What we have found with the old VLANs is that they're generally very effective at containing broadcast traffic. With modern switches, if you have a broadcast storm, it tends to happen on a single VLAN. It doesn't tend to take the whole switch out. This has been quite helpful. And essentially what we've done is we've found a block of VLAN tags which are unique to both exchanges. They don't get used on any other layer 2 fabric connected to either exchange for anything else. But if you start doing these kind of arrangements with more than one layer 2 operator and you start doing sensible block allocation schemes, it's amazing how quickly you start running out of space, particularly because a lot of the equipment out there doesn't even support the full 12-bit VLAN range. So we assigned 100 blocks, 40 to each operator for point-to-point VLANs initiated at their side, and then 20 in the middle for public. There's one for IPv4 public peering, one for IPv6. Some stuff for future growth. We also had to give some thought to the commercial model in this, and really we tried to keep it as similar to inter-ISP sender-keeps-all peering arrangements. There's no settlement across the interconnect for traffic. LUNAT members don't pay exchange point customers don't pay LUNAT. Any commercial arrangements between the parties exchanging traffic are basically not a matter for the internet exchange operators. If people want to buy and sell transit or do paid peering or mutual backup arrangements or whatever, then that's up to them. Basically, we did give each operator the right to impose their own commercial terms. For example, in the exchange point side, some of our customers, we charge extra for extra VLAN assignments. But the basic principle was to preserve the autonomy of both operators, but to keep it simple. We have thought about other commercial models, particularly where the exchange we might be connecting to is also a commercial one. You can do things like revenue sharing or resale arrangements, but they weren't appropriate for the particular relationship between exchange point and LUNAT. Resilience in practice. As I said, spanning tree is really not practical. In terms of multiple spanning tree domains, 802.1s may change this in future, but it's not a standard that's widely implemented by many switch vendors at this point in time. Basically, spanning tree is too hard, too dangerous, we prohibited it across the interconnect. There is some resilience. We actually have 4 physical interconnects in place. One of them is for the public VLAN, one for the private VLANs. 2 are basically shut down for manual enablement. And if people really want resilience, if you want a service level to a party that you're peering to through these kind of arrangements, then basically connect to both exchanges. Don't rely on fancy complicated stuff between the two to make your connection resilient, because it's just not going to work. There was also the question of acceptable use. Again, we took a very simple approach to this. Both exchanges had well-defined acceptable use policies. Anything that went across the interconnect has to conform to the acceptable use of both. We also said that all traffic must be explicitly VLAN tagged, no untagged default traffic. And essentially obligations of both operators to make sure that anyone who was using the interconnect was aware of the AUP on the other side as well as the local side, and a responsibility on all parties to notify all parties in the event of a breach, and sanction, which could be on a per mode basis, not just pulling the plug in the whole thing. Service levels I've talked a little bit about already. Again, there is no responsibility on either operator for service level on the other side. Basically provide 24/7 contact to the other operator. If a participant is an issue, they should raise it with their own operator first. Operators then report faults to each other and have an obligation to circulate maintenance tickets and the like. You'll see that the agreement, which basically documents all the above, is in the public domain. We also added a schedule which basically said that, which basically has got all the nitty-gritty details that could change over time and that potentially you don't want in the public domain because they include things like escalation points, address range assignments, VLAN tag assignments, these kind of things are on our schedule, which is viewable on the private web pages of each operator. And there are also pages which are accessible to all participants, listing things like VLAN assignments, who's been assigned AS numbers, IP addresses, who to contact if you want to peer through the interconnect. One or two administrative considerations. Is an agreement of this nature legally binding? We've found a convenient way to sidestep that. Is there a termination notice period? Effectively what we did is said that every 6 months we will conduct a review and basically decide to continue the agreement depending on traffic levels. There's also collector routers. Is this something that we want to put in there? There's one on the LAN app side. We have plans to put one on the exchange point side as well, basically just so that we can see what routes are available at the shared public. One or two open issues. Yes, we know that broadcast storms can get through. In general, when we had the particular recent incident, what happened was that everyone who was connected to the public exchange was impacted, but also people who were connected to both exchanges were impacted as well. It seems to be an increasing practice that people use the same router to connect to multiple exchanges, so actually I don't think that was too bad. I don't think that makes things significantly worse. We haven't quite figured out how to maintain a mailing list that is updated one half of participants on each side locally, but can be also posted to by either side. I'm sure that's not a hard problem to solve. Some switch vendors use VLAN 1 as the default VLAN for carrying BPDUs in. This is a little bit difficult on Cisco switches because you can't turn that off. VLAN 1 is on every port. You can't disable that. We didn't think we had a problem with extreme switches until we switched to 802.1w, and we found that we were forced to use VLAN 1 as well. Another interconnect mode that we've looked at is extending the reach of one operator to buildings that they're not in, but which the other operator is in. There's also an interesting question. Why should an ISP who is connected to both exchanges continue to connect to both when they can save money by only connecting to one? Really, the best answer we have for that is the service level points that I made before. One or two observations. We very much needed a champion of this in each organization. There was quite a lot of resistance and suspicion. And that wasn't just about, from a commercial bottom line point of view, will these guys take our business away, will we lose revenue? It was also about, on the membership organization side, well, exactly why are these commercial guys doing this? I think that we stuck with it. I think that both communities, in the broadest sense, in terms of participants, members, customers, operators, see that there's mutual benefit there. The other thing is, when we sat down and started writing the agreement, I thought it could be very easy to be extremely prescriptive here and have pages and pages and pages of how to do this, but I don't think that having a really complex prescriptive agreement actually helps. It's better to keep things simple. And my final point is that really additional switch and router vendor features would make life a hell of a lot easier, not just in this interconnect of two exchanges environment, in the more general layer 2 environment. Those of you who work for switch vendors have probably heard all this before, but I'm going to take a chance to say it again. There's actually a small number of features which make life an awful lot easier. Protection against broadcast storms. At an internet exchange, really there is no broadcast traffic that has any business being there apart from ARP packets. More than 100 ARP packets, broadcast packets per second is an abnormal condition. It should be possible to filter right down to do that. In practice, a lot of the switch hardware out there doesn't have that granularity on its filtering. Some of the software-based switch filtering potentially can do this. Also, there's the simple ability to, if an ARP packet doesn't have the IP address range that is the public peering mesh, then it should be dropped with the switch. More powerful features to deal with alien BPDUs, whether they're being rejected or ignored or blocked or transparently carried, or whether you shut down the port if you see them. These would all be really useful. Also, the ability to detect loops better than spanning tree technology does. It's a bit of a bodge, but what would be really useful is the ability to monitor and diagnose the intermediate layer 2 hops. One of the better ways of doing, I've seen this, is the MARP standard. Basically, the idea that you can tell a switch that these MAC addresses are important, tell me if they disappear from your forwarding database. Or maybe you get a whole bunch of really cheap and cheerful IP probes that you can ping, and you just glue them at intermediate points along the circuit onto that circuit to see and try and diagnose where the failure is. Other things on my wish list, if we had a better selection of entry-level BGP-capable routers as opposed to below a certain price limit, your only option being a Zebra PC, I think people would be less inclined to use switches when they should be using routers. VLAN tools, tag remapping, some switch vendors support this. This is actually quite useful in terms of reusing the VLAN tag space. I suspect that this is propagating, using an evil to solve an evil, have a larger number space for VLAN tags, more than 12 bit. Maybe a registry somewhere keeping track of all this stuff might actually be a useful tool. And also, those carriers of you who are offering distance peering services, I don't see any reason why broadcast traffic needs to be forwarded across these services. Being able to spoof the broadcast for the remote IP address locally in the device that's actually attached to the exchange would potentially reduce the risk of broadcasts getting to places where they shouldn't be. So, in conclusion, Layer 2 interconnect can be a good idea where it makes the internet scale better. It seems to me the most obvious place where this makes it scale better is where we have coterminous IXPs, and it's done on a formal, regulated, reasonably controlled and well understood basis. Where it's being done to connect switch fabrics together on an arbitrary basis over complex topologies, over long distance using intermediate non-transparent technology, sure, it's going to save you money, but it's going to make the internet as a whole more complex and less stable. A few presentations up there, as well as this one. There's a couple of presentations that I've given on this topic previously at Wright meetings. Finally, I'd just like to acknowledge and thank James Rice at LUNAP for his help in putting all this together and his cooperation in making it happen. Happy to take any questions.
Just talk.
Question? Hello? As an exchange point operator, I'm just curious what your thoughts are on the notion of a separate critical mass or separate VLAN. We get just about every kind of suggestion known to mankind on how people want to connect to our exchanges. And one thought that had occurred to a couple of our participants was that rather than invest a lot of energy in all of the protections for all these issues over distance peering, would be to actually establish separate VLANs or separate exchanges that are dedicated for distance peers. Maybe instead of it could be on the same switch, but more than likely on a separate device, and then co-located participants could take advantage of those distance peers with a separate exchange port. I'm just curious to know from your experience, particularly in Europe, do you think people would buy into that? And secondly, do you think it's really worth the effort, given all the steps that you've just mentioned and all the risks for interconnecting exchanges is it easy enough to protect that you shouldn't bother?
The single biggest problem with that in practice, yeah, I agree, it's a good idea, it's one that we're considering, but the single biggest problem in practice is how do you tell what the customers actually got connected? You can have a box connected to your exchange, which is a third-party router, which happens to be bringing in a connection from another participant. The way that we were thinking of implementing that was on a kind of shoot first, ask questions later basis, which is that in a conventional public exchange, you see somebody injecting BPDUs or odd weird broadcast traffic, you give them a call, you say, can you fix this? Maybe with a VLAN which was dedicated to non-native router connections, if you saw any of that stuff, the default way would be shut it down, because effectively by opting anybody into that, you would be on the basis of there's a much stricter set of rules for joining this club. So yes, it's something we're thinking about. I haven't had a lot of feedback from ISPs on whether they'd be interested in that.